Hello everyone, welcome to our STEM research project. The title of our project is Adaptive IMM Kalman Estimation for Predictive Interception Using Vision-Guided Robotic Arms. This is the visual context of the predictive tracking. Real-time estimation, intercepting maneuvering targets with low-cost hardware requires a radical shift from reactive to predictive control. Our system integrates multi-model fusion to bridge the gap between high-latency vision inputs and precise robotic execution. Introduction. Our research proposes an optimized adaptive IMM estimation system for robotic arms, integrating the parallel Kalman filter banks, innovation-based noise tuning, and uncertainty-aware motion planning via a high-performance ESP32 microcontroller. This research analyzes the revolution in interception precision for affordable robotics through the introduction of new hybrid concepts used effectively to make the system as robust and predictive as possible under realistic conditions. Our research question is how can an IMM estimator and a low-cost robotic arm be integrated into a single fault-tolerant interception system? We are mainly focusing on the optimal adaptive control logic required to minimize the target RMSE during dynamic maneuvers and sensing latency. This is a picture of our low-cost robotic arm. As you can see, the components all that are used in this robotic arm are amounting to less than $50, giving it the low-cost attribute. Literature review, failure modes, single model mismatch, standard filters, for example, CV or CA, lag critically during directional shifts, producing systematic bias, sensing latency, vision processing delays cause robots to react to stale info, which ends up in them missing the targets entirely, fixed horizon bias, static arm motion times ignore, distance to target variations causing over or undershoot. The research gap that our research fills is no prior work has integrated the high field IMM enhancement with closed loop PID and uncertainty aware planning on sub 50 servo platforms. The aims of our research is mainly to maximize interception success, which is achieving covertness and effective signature management via the IMM, the automated control logic, smart switching between CV, CA, and maneuvering models using our probabilistic weights, efficient tuning online noise adaptation via IAE to handle vibration and lighting shifts, uncertainty management, covariance propagation to select the optimal time window for grasping.
Thank you, Faik. I'm Mahibal Mamun, and now I'll take you through our methodology and system architecture. Our hardware is deliberately minimal, and an ESP32 microcontroller as the central processor, an overhead RGB camera for vision guidance, and a 4-degree of freedom servo arm using actuators. The estimation runs in Python with OpenCV on a laptop communicating to the ESP32 over serial communication. We have kept costs under $50 specifically to demonstrate that high-performance estimation doesn't necessarily require expensive hardware. Now, to our methodology overview. Our methodology has 3 core pillars, as you can see. Firstly, the IMM core, which has 3 parallel filters. Next, we have the IAE tuning, which basically works in a adaptive Q matrix noise estimation. And finally, the optimal planning, which is an uncertainty-aware covariance decision. Next is our optimized IMM architecture. The IMM strength is its parallel architecture. The CV filter is our baseline for both smooth and predictable motion. The CA filter handles gradual acceleration. The maneuver filter uses a high process noise Q, making it fast to respond to sudden changes. Next, we have an online noise adaptation, which is IAE. The second pillar is IAE. In a standard Kalman filter, the process noise matrix Q is fixed. If the environment changes, vibrations, lighting shifts, unmodeled dynamics, the filter can diverge. Our implementation monitors the innovation sequence, and if it grows unexpectedly, Q is enlarged dynamically. The adaptation rate alpha between 0.9 and 0.98 controls how fast the self-correction happens. This makes our system robust to environmental disturbances without any manual returning. Next, we have the uncertainty-aware planning. The third pillar is how we choose when to intercept. Rather than picking a fixed grab time, we propagate the fused covariance matrix towards the fused covariance matrix across candidate intercept windows and select the one that minimizes both positional uncertainty and predicted error. This is critical during model transitions when the IMM is switching between models as uncertainty temporarily increases. Our planner waits for that transition to settle before committing the arm. So as a result, we have made a very small amount of time and a large gain in accuracy. Next is our dynamic arm motion. For the arm itself, we estimate the required motion time using trapezoidal velocity profiles, real physics based on distance, maximum acceleration, and maximum velocity. Next is our input and MCU processing. Putting it all together, the camera extracts the target centroid in 2D pixel space by using OpenCV in Python, as we've already said, which is then converted to 3D world coordinates. This feeds into the Python IMM module on the laptop, which then computes the optimal intercept point, and then this command is sent to the ESP32 and it is converted into PWM signals. And next, our PID loop runs to make sure that the system has as much of an efficiency as possible. Next is our logic diagram. So here you can easily see how the entire process works, what are the logics behind it, and just basically how the actuator works through our codes.
Thank you, Mahi, for his wonderful explanation. For Ramanpurna, I would like to present our simulation results. The headline results are the mean root mean square error of 0.318 pixels and a standard deviation of 0.031 and an interception rate above 95% across our 50 Monte Carlo trials are competitive with systems running on far more powerful hardware. Let me show you on what's driving these. Okay, and these are the relevant equations. They are the key mathematical foundations, the IMM mixing, the Kalman predict update, the IAE adaptation, modifying Q from the innovation square, and the covariance propagation of intercept selection. The standard Kalman theory, and we are actually making it better by our contribution in integrating all this at the same time on a microcontroller with online adaptation. Here you can see this shows what happens when a single constant velocity filter during a sudden acceleration. So as you can see, it tracks smooth motion well, but visibly lags the moment the target maneuvers. So this isn't a tuning problem. The model itself is wrong for the maneuvering model. This is the fundamental limitation of our IMM address. So suppose a car is moving on a constant velocity, and if you use this maneuver model for using on any type of maneuver or like any type of multi-direction, it wouldn't be able to track it properly. So that is why we are supposing another model. So this is the IMM 3D model tracking. So here you can see, compare the previous one to this. The IMM closely follows the true trajectory between the smooth and the maneuvering phases. As the acceleration starts, the maneuver model's weight surges, shifting the blended estimate towards it faster. And that is our adaptive prediction. This result is more accurate throughout the tracking. And here you can see the model probability traces. This makes the switching qualitative. The constant velocity dominates in the linear phases, as you have already seen. But around steps 25 to 55, the maneuver model searches, correctly identifying the regime change, and then the constant velocity is restored. This happens automatically, no human tuning, consistent with what the previous research have been done with Barr and Sloan in 1988. Here you can see the Monte Carlo root mean square distribution. These histograms show how the RMSE across the 50 trials, and the IMM is the one in blue, and it is tight with no outliners. And the CV is orange and has a long right trail, as you can see, and it is catastrophic failures during maneuvers. In real-time intercept scenarios, those outliner are the misses. The IMM has successfully been able to remove them. Okay, the dashed green line is the IMM prediction extrapolated forward, and the red, X mark in red is the predicted intercepted at approximately the coordinates 97 and -27. And the planner choose this moment by minimizing both the positional error and uncertainty, not just where it will be, but where can we be confident it will be. Like it already defines the value itself. So that is already a step up from our previous models. And now you can see the experimental data summary. The table confirms that the IMM has the lowest mean RMSE and the lowest standard deviation and the tightest range. The model is consistently avoiding the outliner events. The maneuver filter overcorrects in smooth phases and CV fails hardest during maneuvers. The IMM suits unambiguously at the top. Okay. And here we can see the comparative tracking accuracy. The bar chart makes it visual. The IMM success rate is highest, driven by outliner avoidance. In robotics, reliability matters more than average performance. And that is what you can see exactly on this show. And the results show that the IMM isn't just more accurate, it's more trustworthy. And that was my part. And now I'd like to hand over Sougota to say the rest of the part. Thank you.
Thank you, Farhan. I'm Sougota Banik, and I'll close with our discussion limitations and future directions. Our validated successes are clear: empirical confirmation of outlier avoidance, successful decoupling of sensing latency from prediction accuracy, and a Monte Carlo success rate above 95%. But science requires honest accounting of constraints. Two remain. First, our simulation assumes planar 2D motion. A real 3D environment requires stereo or depth camera extension, adding both cost and computational load. Second, servo backlash. The mechanical play in low-cost servos is not modeled. At the precision levels we're targeting, that compliance matters and needs to be characterized physically. The next slide. Here, As a research summary, we are to summarize, this research demonstrates that adaptive IMM estimation is a viable, high-performance successor to the single model filtering, even on severely constrained hardware. The two key technical achievements are probabilistic multi-model fusion, which correctly identifies dynamic regimes and eliminates outer interceptions, and IAE-based online tuning, which allows the system to remain accurate under changing environmental noise without manual recalibration. Our results confirm that the estimation layer is no longer the bottleneck. The path forward is hardware improvement. Now, for the next slide, future work. We see three clear directions for extending this work. First, a 3D extension using stereo cameras or depth sensors, the most direct path to the real-world deployment. Now, the second one is deep learning integration, replacing the centroid-based tracker with a CNN such as YOLO would give us object class aware tracking and robustness to occlusion. Now, for the third, the multi-target tracking, extending the IMM framework to simultaneously estimate and intercept multiple objects, opening up applications in swarm robots and multi-agent systems. Thank you all for your attention. For those interested in the technical details, our paper covers the full mathematical derivation, simulation code, and result tables. We believe this work shows that high-performance state estimation is genuinely accessible on low-cost platforms, and we hope it opens the door to the future work in this space.